Okay, so far we have been deriving functions, or equations, I guess, that are explicitly solved for y. For instance, everybody can derive something like this, x squared. You know what, I'm going to go ahead and make this one step further, and let's rewrite it as sine of x squared. Okay, similar functions. Let's say we wanted to derive both of these. Well, what we're doing when we derive is we're really deriving the left side and the right side of this equation. It just happens that when we derive the right hand side, we get 2 times x. When we derive the left hand side, well, we get the derivative of y with respect to x. We write that as the derivative of y with respect to x. Alright, now really, you might have seen this before. What you're doing there is you're doing the derivative with respect to x of y. Well, we just rewrite that as we pretend this y is over 1, okay, and we pretend like we're multiplying, even though we're really not, and you get d times y over dx. But it's not really multiplying, it's just that's just the way that we use the notation here, but we write it as dy over dx. Okay, now let's take a look at deriving this one over here, and notice some difference here. When we derive the left side, we still get dy over dx, the derivative of y with respect to x, and over here we still do the power rule. We bring down that 2, so it's 2 times times sine of x to the first, and we multiply that by the derivative of the inside, which is, I'm squeezing it in there, cosine of x. Okay, so we have to tack on this second part here because of the chain rule. Well, that's really happening over here in this example as well. When we derive when we derive x squared, what we're really doing is we're doing power rule, 2 times x to the first, and then we're multiplying by the derivative of what's inside of that power, that's squared. Well, it's just x. But everybody knows that the derivative of x is just 1. When you derive x, you get 1. So really we're doing the chain rule. But the main point that I'm trying to bring up here is that the fact that the derivative of x is 1, because that's really the derivative of x with respect to x. It's just this fraction right here. Well, that's just 1 every single time. But when you derive y, you don't get 1. You get dy over dx. That doesn't simplify down to 1. The derivative of x does. You get 1. Okay, that would also happen over here. We'd have to derive what's inside of that or the sine function, because we derive the power, 2 to the first. Then we derive the inside part, that's sine, turns into cosine. Then we derive what's inside of sine. Well, that's x. So technically, even though I'm not going to write it like next to there, because we're lazy, there's a 1 there. We're deriving the inside. Inside of x, deriving that is 1. But the reason that's 1 again is because of this dx over dx. So main rule here that we're looking at is when you derive y, you get dy dx. When you derive x, you get 1. But that's only happening because we are deriving with respect to x. So check this out. If we were to derive, I'm just making this up here. If we were to derive y equals x, let's make it x squared again, with respect to t. Okay, now t is not even in there, okay, but t is just some variable that we can derive with respect to, and t is arbitrary. You can call it t, l, p, whatever. Okay, if we derive with respect to t, now when we derive that left side, we don't get dy dx, we get dy, the change in y, with respect to the change in t. When we derive this x squared, we derive it like normal. We get 2 times x to the first times the derivative of what's inside. But now the derivative of what's inside here, this x, is no longer 1, because it's not dx over dx. It's dx over dt. So that would be the derivative with respect to t. And again, t was completely arbitrary. I can call that any letter I want. Let's say we want to derive it with respect to, I don't know, what's your favorite letter? W? Mine too. Great. Derive with respect to w. Well, now what changes is the derivative of y with respect to w is not dy dt or dy dx. It's dy dw. When you derive x squared, you get 2x, that's the power rule, times the derivative of what's inside. But the derivative of x with respect to w is dx dw. Okay? So we've seen this dy dx a bunch of times, but that's because we've always been deriving with respect to x. We can derive with respect to any variable, and you'll see that later on when you get to related rates, things like that. But for now, let's stick with deriving with respect to x. So we want to find dy dx here in this section, and what I've done here is given you the same equation, y equals 1 over x, is the same exact thing as x times y equals 1. But let's say we wanted to derive it without simplifying it. So let's say we want to derive this thing right here. So the derivative of y will derive left and right. The derivative of y, you rewrite that as derivative of y with respect to x, dy dx. And over here, 1 over x is just x to the negative 1. So when we derive that, we get, by the power rule, negative 1 times x to the negative 2, which is negative 1 over x squared. So dy dx is negative 1 over x squared. And that's just, again, this negative 1 over x squared gives us the instantaneous rate of change of this graph, of this function, at any x value I choose. I can derive this over here too. I'm just deriving the left side and the right side. There's nothing wrong with me deriving the left side and the right side up here. Check it out. When we derive the left side here, we have to do the product rule, which says derive the first. Let's draw a big line here. When you derive x, you get 1, because that's really, you know what, let's not even write 1 there. When you derive x, you're really going to get dx over dx. That's really what's happening there. Times y plus, leave x alone, the first, derive the second. Well, that's dy dx equals, deriving the right-hand side, the derivative of 1 is 0. The derivative of any constant number is just 0. And now we simplify this. Well, dx dx is 1 times y is just y times x times dy dx. Okay, well, there's nothing wrong with this. My goal is to find dy dx, so I need to solve for dy dx here. And when you do that, you find out that dy dx is negative y divided by x. Subtract y divided by x. So here's our main problem. We derive this equation right here and this equation right here are the same thing. They just look different. They look different. So when we derive it and find dy dx, we should end up with the same thing. Meaning that, let me erase all this crap. Meaning that this dy dx over here, this negative y over x, should be the same exact thing as this negative 1 over x squared. And I'm telling you, I submit here, that it is the same thing. Check this out. If dy dx is negative y over x, well then, dy dx is really negative. Let's put y. What is y? Well, y is just 1 over x. Okay? That's the same thing. If we took this equation right here and solved it for y, we would get y equals 1 over x. Same thing. So y is just 1 over x. So when I rewrite this derivative here, I can make it negative 1 over x. That's y over x. But that simplifies down to negative 1 over x squared, which is the same thing we got over here. So you can see the derivative is still the same, but now it's just in terms of x and y. And there's really nothing wrong with that. And sometimes we're going to have to work with our derivatives in terms of y. Let's take a look at a different example here. Let's derive this thing. Well, we have two options here. We could, since this is kind of easy to solve for y, we could solve for y. And when we did that, we would subtract x squared off both sides. Well, that would give me 25 minus x squared. And then we would take the square root. But remember, when you take the square root of both sides of an equation, you got to make sure that you account for the plus or minus out front. So what that really means is y is not one function. This graph over here, this equation right here, if we graphed it, would not be a function. It would actually be a circle. If you were to graph this equation right here, you would get a circle centered at 0 with a radius of 5. Okay, so it would look like this. Negative 5. There we are. Okay, so it's a circle centered at 0 with a radius of 5. Well, that's not one function. It's two functions. You can see you got the top part and the bottom part, and that's what happens when you solve for y. Positive square root 25 minus x squared would be this part right here, just this part in red. And negative square root 25 minus x squared would be the part on the bottom. So basically, if we want to find dy dx now for this whole thing, we'd have to take two derivatives, the positive and the negative. If we leave it in this form over here, we can just derive it and get a dy dx out without having to do two different derivatives. So check this out. We're going to do it both ways. If we derive this equation over here in the form we were given, you would get the derivative is 2 times x times the derivative of x, which is 1 because we're deriving with respect to x, okay, dx dx, plus deriving y squared now would be 2y times the derivative of y, which is dy dx. And this is just the chain rule happening. You derive the power, then you derive what's inside. Dx over dx in here would dy over dx. And that would equal 0. And dx over dx is really just 1, so this simplifies down to 2x plus 2y times dy dx equals 0. And what that is really going to give us here, let's erase this circle, okay? It looks like a circle. Don't forget that. But when you solve for dy dx, you get that dy dx is negative 2x over 2y, which is really negative x over y. So dy dx is negative x over y. Looks pretty nice. There you go. That's the derivative. Well, what happens if we derive it in this other form? If we solve for y first and derive it? Well, we really have to do two separate derivatives here. We'll derive the positive one. Okay, so let's go ahead and draw this little line here. If y is the square root of 25 minus x squared, when you derive that, you get 1 over 2 root 25 minus x squared, that's the derivative of the square root, times the derivative of what's inside, which is negative 2x. So this is just negative x over the square root of 25 minus x squared. Well, is this derivative we just got, is this the same exact thing as this answer up here? And yes they are, because you can see this. The derivative up here is negative x over y, that's no big deal. And down here we have negative x over this square root thing. But remember, we're saying y equals the positive, right here, y equals the square root of 25 minus x squared. So if we did that substitution, we would get the same exact derivative. This one looks a whole lot nicer. There's no square roots in there or anything. But it works out. Now, let's check out what would happen if we derive the other function, y equals negative square root 25 minus x squared. Well, this would be negative. And when you derived it, you would get negative 2x over 2 root 25 minus x squared. And these two negatives would become a positive. So now, if we derive the negative portion, the bottom part of our circle, which would be this, right here, just the bottom part, our derivative is positive x over the square root 25 minus x squared. Well, this is still the same thing as negative x over y, because y was negative square root 25 minus x squared. If you plug this into this equation up here, the negatives cancel, and you get x over the square root. So the derivatives are the same. And a lot of times you don't need to solve for y. You can just derive it and get this, and now you're done. There's your derivative. But it's important to remember that this fraction here is still the same thing as the derivative, so it still tells us the slope of the graph if you plug in a point that's on that graph. And an easy example of that would be, let's take a look at, our circle looks like this, right? Let's take a look at when you plug in x equals 3. Well, there's 2 points when x equals 3. There's a point up here, and there's a point down here. Okay, so let's change this. Find dy dx if x is 3. Okay, so I'm changing the problem. If x is 3, find dy dx. Okay, well, I already found dy dx. It's right here, negative x over y. So that's no problem. I know x is 3, but the problem is now there's more than one point when x is 3. There's 2 points. There's one up here, and there's one down here. We've got to find both those y values. We know that this point is 3 something, and we know this point down here is 3 something. We've got to find the y values. Well, if this equation is true, x squared plus y squared is 25, then when x is 3, you get 9 plus y squared is 25, and if you solve that, you get y is equal to plus or minus 4. So that's a y. So it must be true that this point here is 3, 4, and this point here is 3, negative 4, right? Well, there's nothing wrong with that. The slope when x is 3, well, there's 2 different points, so we're going to have 2 different slopes, and you have to specify that. dy dx, the derivative, at the point 3, 4, that's equal to negative x, that's negative 3, over positive 4, negative 3/4. You can see on this circle the slope is negative there. The slope has a negative direction, so negative 3/4 works out. dy dx at my other point, when x is 3, at the point 3, negative 4, well, that's negative x, that's negative 3 over negative 4, which is y. Well, that is 3/4. And that should make sense. You can see that the circle's symmetric, so it should have the same slope at this point and at this point down here, 3, negative 4. And it does. It's just that one's going up and one's going down. So the point down the bottom here, 3, negative 4, has a positive slope of 3/4. The point up here has a negative slope at 3/4. And you would find the same exact answer if you had derived this y equals equation. If you solve for y and derive it that way, you're going to find the same thing. So, main idea, you can derive without solving for y, and you can still find the derivative. It still represents the slope of your graph at that point. It's just now there might be more than one y value for each x value, because it doesn't have to be a function anymore now. So you might have to find the y value to find the slope at the point you're interested in. So if they just say if x equals 3, well, sometimes you got to find what the y value is. There might be more than one, so there might be more than one dy dx at x equals 3, because there's more than one point. That's what we just showed here. All right. And sometimes they will ask you, they, me, book, teacher, whoever, will ask you to find the second derivative. This whole scary looking d squared y over dx squared, here's what that means. When we derive something with respect to x, we're really doing d dx of that thing. Okay, so we really do d dx of y. But we write that in shorthand as dy dx. Well, if you want the derivative of the derivative, that's called the second derivative, well then you really want d dx of dy dx. Well, using our same idea that we can treat this like it's multiplication, even though it's not, it's kind of just weird notation, d dy, they rewrite that as d squared y up top, and dx dx makes dx squared. But all that is the derivative of the derivative. So, to find the second derivative, we just want to derive this thing twice. And there's a bunch of different notations that they can give you to find second derivative. Okay? Instead of asking for dy dx or d squared y over dx squared, they could say find y double prime. That means the second derivative. It's y prime prime. So, anyway, to find the second derivative, the first thing we got to do is find the first derivative. So, let's go ahead and do that. Deriving this thing with respect to x will give us 2/3 x to the negative 1/3 times the derivative of what's inside of that, which is just 1, dx over dx, plus the derivative of y to the 2/3 is 2/3 y to the negative 1/3 times the derivative of what's inside of that, which is dy dx. The derivative of y is dy dx. So basically, anytime you derive a y with respect to x, you derive it, treat it just like it's like a regular old variable, treat it like it's x, 2/3 y to the negative 1/3, but then you multiply by dy dx, because you are deriving the inside of this 2/3 power, and that's y, and that turns into dy dx. And that's going to equal, deriving the right-hand side here is 0. So now we want to solve for dy dx. So what I'm going to do is subtract off 2/3 x to the negative 1/3. Okay, so that's going to give us 2 over 3y to the 1/3 dy dx is equal to negative 2 over 3x to the 1/3. Okay? And since I want dy dx here, I'm going to multiply this entire side by 3 over 2y to the 1/3. And I'm the same thing over here. I'm multiply by 3 over 2y to the 1/3. What? No. Come on now, Mr. Smith. You're getting all crazy. No. We're multiplying by 3y to the 1/3 over 2. The reciprocal of what we don't want there. So over here I'm going to multiply by 3y to the 1/3 over 2. There we go. And what happens over here is these things all cross out, and we're left with dy dx is equal to, and here the 2's cancel, the 3's cancel, we get negative y to the 1/3 over x to the 1/3. That's the first derivative. That is dy dx. That will tell us the slope of the function at any point we plug in. But notice again, it depends on y. So there's nothing wrong with that. Just that they gave us an x value, we'd have to use our original equation to find the y value that corresponds with that x value. But we really want the second derivative, so what we're going to do now is derive this thing again. And you write it like this. The second derivative of y with respect to x is, now to derive this thing, it's a little annoying, but we got to do the quotient rule, because it's a fraction, it's a quotient. So the quotient rule says low x to the 1/3 times d high. Well, the derivative of the top is negative 1/3 y to the negative 2/3 times dy dx. You got to derive the inside of that to the 1/3, and that's y is inside of there, so the derivative that's dy dx. So minus high d low, well, high is negative y to the 1/3, so that becomes plus y to the 1/3 times the derivative of the bottom. Well, that's 1/3 x to the negative 2/3. And that's all over low squared. That's x to the 2/3. So that's the second derivative. It looks really scary, right? We're going to simplify this down, just be as neat as possible here. What we've got going on first off is that I want to rewrite these negative exponents in my denominator, okay? So I'm just going to go ahead and do that. This y to the negative 2/3 really just moves down to the denominator of this fraction here. You can't move it all the way down to the bottom of the big fraction because there's this big plus here. So it really just goes down into its own little fraction. And this x to the 1/3, I'm just going to put that on top here. Okay, we're just multiplying by x to the 1/3 in here. So that's just going to land up here. X to the 1/3. And this is still times dy dx. Over here, this fraction, y to the 1/3 times 1/3 x to the negative 2/3, that's going to simplify down to, when you put it all together, y to the 1/3 over 3x to the 2/3. So that's a little bit nicer. And also, you never ever ever leave dy dx in your answer. You plug back in what dy dx is. Well, dy dx is this fraction here, negative y to the 1/3 x to the 1/3. So I'm going to sub him out. Say, get out of here, dy dx. I'm going to sub in what dy dx is, which is negative y to the 1/3 over x to the 1/3. And now I'm just going to simplify this stupid thing. So although it's kind of annoying, we're past calculus at this point. We're just trying to derive it. Not derive it, simplify it. So we're just doing a little bit of algebra. And we find out that the second derivative of y with respect to x is, multiplying this fraction here, gives us positive, x's cancel. So it's positive 1 over 3. And y to the 1/3 is going to cancel with y to the 2/3 here. So we're going to end up with y to the 1/3 on the bottom. There we go. And that's plus y to the 1/3 over 3x to the 2/3 all over x to the 2/3. Alright, so we're not done yet. We're still simplifying. We know we don't want this complex fraction going on here, so we got to simplify this fraction. Nothing wrong with that. What we're going to do to simplify this fraction is we're going to multiply through by the common denominator, which is 3 y to the 1/3 x to the 2/3. So I'm going to multiply through by 3y to the 1/3 x to the 2/3 on the top and the bottom, because I don't want these complex fractions in there. And when I do that, what I'm going to end up with for my second derivative is d squared y over dx squared. When I multiply all this junk to this fraction, the 3y to the 1/3 cancels, and we're just left with x to the 2/3. Plus, when I multiply it into this fraction, well, the 3 and the x to the 2/3 cancel. So I have y to the 1/3 right here, times this y to the 1/3, and that's y to the 2/3. And on the bottom, we have 3y to the 1/3 x to the 2/3 times x to the 2/3. So that's going to be 3, I'm going to put x first, x to the 4/3, because you add up the exponents there, times y to the 1/3. And there you go. That's a perfectly fine second derivative. And if you're checking your answer in the back of a book or something, or in your teacher's worksheet, usually, this does not happen all the time, but usually the problems they choose for students to find the second derivative of, usually they simplify down a little bit further, because what you can do at this point is look back at the original equation we started with, which was x to the 2/3 plus y to the 2/3 equals 4. And usually you'll see part of that pop up somewhere. And look, x to the 2/3 plus y to the 2/3, that's right there. Well, that equals 4. So that whole numerator just becomes 4 over 3x to the 4/3 times y to the 1/3. And all this derivative here represents, it's the first derivative of the first derivative. That's it. So it's the second derivative of our original function.